Good morning, good evening, and good afternoon, everyone. Welcome to this MapReduce tutorial where we will learn about MapReduce, how it works, what is MapReduce, and what are the benefits of using MapReduce. So, MapReduce is basically a programming model, or you could also say it's a processing framework, although for processing framework, yarn would be the right word to use, and MapReduce is a programming model. So we'll understand about MapReduce analogy. What is Hadoop MapReduce? What do you mean by parallel processing in MapReduce? Hadoop MapReduce workflow, and then finally we would have a demo on MapReduce. Now, suppose you have a library that has a collection of huge number of books on each floor, and you want to count the total number of books present on each floor. What would be your approach? You could say, I will do it myself, but then don't you think that will take a lot of time? And that's obviously not an efficient way of counting the number of books in this huge collection on every floor by yourself. Now, there could be a different approach or an alternative to that. You could think of asking three of your friends or three of your colleagues, and you could then say if each friend could count the books on every floor, then obviously that would make your work faster and easier to count the books on every floor. Now, this is what we mean by parallel processing. So when you say parallel processing in technical terms, you're talking about using multiple machines, and each machine would be contributing its RAM and CPU cores for processing, and your data would be processed on multiple machines at the same time. Now, this type of process involves parallel processing in our case, or in our library example, where you would have person 1 who would be taking care of books on floor 1 and counting them, person 2 on floor 2, then you have someone on floor 3 and someone on floor 4. So every individual would be counting the books on every floor in parallel, so that reduces the time consumed for this activity. And then there should be some mechanism where all these counts from every floor can be aggregated. So what is each person doing here? Each person is mapping the data of a particular floor, or you can say each person is doing a kind of activity or basically a task on every floor, and the task is counting the books on every floor. Now then you could have some aggregation mechanism that could basically reduce or summarize this total count, and in terms of MapReduce we would say that's the work of reducer. So when you talk about Hadoop MapReduce, it processes data on different node machines. Now this is the whole concept of Hadoop framework, right? That you not only have your data stored across machines, but you would also want to process the data locally. So instead of transferring the data from one machine to other machine, or bringing all the data together into some central processing unit and then processing it, you would rather have the data processed on the machines wherever that is stored. So we know in case of Hadoop cluster, we would have our data stored on multiple data nodes on their multiple disks, and that is the data which needs to be processed. But the requirement is that we want to process this data as fast as possible, and that could be achieved by using parallel processing. Now, in case of MapReduce, we basically have the first phase, which is your mapping phase. So in case of MapReduce programming model, you basically have two phases. One is mapping and one is reducing. Now, who takes care of things in mapping phase? It is a mapper class. And this mapper class has the function which is provided by the developer, which takes care of these individual map tasks which will work on multiple nodes in parallel. Your reducer class belongs to the reducing phase. So a reducing phase basically uses a reducer class which provides a function that will aggregate and reduce the output of different data nodes to generate the final output. Now that's how your MapReduce works, using mapping and then obviously reducing. Now you could have some other kind of jobs which are map only jobs, wherein there is no reducing required. But we are not talking about those. We are talking about our requirement where we would want to process the data using mapping and reducing, especially when data is huge, when data is stored across multiple machines, and you would want to process the data in parallel. So when you talk about MapReduce, you could say it's a programming model. You could say internally it's a processing engine of Hadoop that allows you to process and compute huge volumes of data. And when we say huge volumes of data, we can talk about terabytes, we can talk about petabytes, exabytes, and that amount of data which needs to be processed on a huge cluster. We could also use MapReduce programming model and run a MapReduce algorithm in a local mode. But what does that mean? If you would go for a local mode, it basically means it would do all the mapping and reducing on the same node using the processing capacity, that is RAM and CPU cores, on the same machine, which is not really efficient. In fact, we would want to have our MapReduce work on multiple nodes, which would obviously have mapping phase followed by a reducing phase, and intermittently there would be data generated. There would be different other phases which help this whole processing. So when you talk about Hadoop MapReduce, you are mainly talking about two main components or two main phases, that is mapping and reducing. Mapping taking care of map tasks, reducing taking care of reduced tasks. So you would have your data which would be stored on multiple machines. Now when we talk about data could be in different formats. We could, or the developer could specify what is the format which needs to be used to understand the data which is coming in. That data then goes through the mapping. Internally there would be some shuffling, sorting, and then reducing, which gives you your final output. So the way we access data from SDFS, or the way our data is getting stored on SDFS, we have our input data which would have one or multiple files in one or multiple directories, and your final output is also stored on SDFS to be accessed, to be looked into, and to see if the processing was done correctly. So this is how it looks. So you have the input data which would then be worked upon by multiple map tasks. Now how many map tasks? That basically depends on the file. That depends on the input format. So normally we know that in a Hadoop cluster you would have a file which is broken down into blocks depending on its size. So the default block size is 128 MB, which can then still be customized based on your average size of data which is getting stored on the cluster. So if I have really huge files which are getting stored on the cluster, I would certainly set a higher block size so that my every file does not have huge number of blocks creating a load on name nodes RAM, because that's tracking the number of elements in your cluster or number of objects in your cluster. So depending on your file size, your file would be split into multiple chunks, and for every chunk we would have a map task running. Now what is this map task doing? That is specified within the mapper class. So within the mapper class you have the mapper function which basically says what each of these map tasks has to do on each of the chunks which has to be processed. This data intermittently is written to SDFS where it is sorted and shuffled, and then you have internal phases such as partitioner which decides how many reduce tasks would be used or what data goes to which reducer. You could also have a combiner phase which is like a mini reducer doing the same reduce operation before it reaches reduce. Then you have your reducing phase which is taken care by a reducer class, and internally the reducer function provided by developer which would have reduce task running on the data which comes as an output from map tasks. Finally, your output is then generated, which is stored on SDFS. Now, in case of Hadoop, it accepts data in different formats. Your data could be in compressed format, your data could be in Parquet, your data could be in Avro, text, CSV, TSV, binary format, and all of these formats are supported. However, remember, if you're talking about data being compressed, then you have to also look into what kind of splittability the compression mechanism supports. Otherwise, when MapReduce processing happens, it would take the complete file as one chunk to be processed. So SDFS accepts input data in different formats. This data is stored in SDFS, and that is basically our input, which is then passing through the mapping phase. Now what is mapping phase doing? As I said, it reads record by record. Depending on the input format, it reads the data. So we have multiple map tasks running on multiple chunks. Once this data is being read, this is broken down into individual elements. And when I say individual element, I could say this is my list of key value pairs. So your records based on some kind of delimiter or without delimiter are broken down into individual elements, and thus your map creates key value pairs. Now these key value pairs are not my final output. these key value pairs are basically a list of elements which will then be subjected to further processing. So you would have internally shuffling and sorting of data so that all the relevant key value pairs are brought together, which basically benefits the processing. And then you have your reducing, which aggregates the key value pairs into set of smaller tuples or tuples, as you would say. Finally, your output is getting stored in the designated directory as a list of aggregated key value pairs, which gives you your output. So when we talk about MapReduce, one of the key factors here is the parallel processing which it can offer. So we know that our data is getting stored across multiple data nodes, and you would have huge volume of data which is split and randomly distributed across data nodes, and this is the data which needs to be processed. And the best way would be parallel processing. So you could have your data getting stored on multiple data nodes or multiple slave nodes, and each slave node would have again one or multiple disks. To process this data, basically we have to go for parallel processing approach. We have to use the MapReduce. Now let's look at the MapReduce workflow to understand how it works. So basically you have your input data stored on SDFS. Now this is the data which needs to be processed. It is stored in input files, and the processing which you want can be done on one single file, or it can be done on a directory which has multiple files. You could also later have multiple outputs merged, which we achieve by using something called as chaining of mappers. So here you have your data getting stored on SDFS. Now input format is basically something to define the input specification and how the input files will be split. So there are various input formats. Now we can search for that. So we can go to Google and we can basically search for Hadoop MapReduce Yahoo tutorial. This is one of the good links. And if I look into this link, I can search for different input formats and output formats. So let's search for input format. So when we talk about input format, you basically have something to define how input files are split. So input files are split up and read based on what input format is specified. So this is a class that provides following functionality. It selects the files or other objects that should be used for input. It defines the input split that break a file into tasks, provides a factory for record reader objects that read the file. So there are different formats if you look in the table here, and you can see that the text input format is the default format, which reads lines of a text file, and each line is considered as a record. Here the key is the byte offset of the line, and the value is the line content itself. You can have key value input format, which parses lines into key value pairs. Everything up to the first tab character is the key, and the remainder is the line. You could also have sequence file input format, which basically works on binary format. So you have input format, and in the same way you can also search for output format, which takes care of how the data is handled after the processing is done. So the key value pairs provided to this output collector are then written to output files. The way they are written is governed by output format. So it functions pretty much like input format as described in earlier, right? So we could set what is the output format to be followed, and again you have text output, sequence file output format, null output format, and so on. So these are different classes which take care of how your data is handled when it is being read for processing, or how is the data being written when the processing is done. So based on the input format, the file is broken down into splits, and this logically represents the data to be processed by individual map tasks, or you could say individual mapper functions. So you could have one or multiple splits which need to be processed depending on the file size, depending on what properties have been set. Now once this is done, you have your input splits which are subjected to mapping phase. Internally you have a record reader which communicates with the input split and converts the data into key value pairs suitable to be read by mapper. And what is mapper doing? It is basically working on these key value pairs, the map task, giving you an intermittent output which would then be forwarded for further processing. Now once that is done and we have these key value pairs which is being worked upon by map, your map tasks as a part of your mapper function are generating your key value pairs, which are your intermediate outputs to be processed further. Now you could have, as I said, a combiner phase or internally a mini reducer phase. Now combiner does not have its own class. So combiner basically uses the same class as the reducer class provided by the developer, and its main work is to do the reducing, or its main work is to do some kind of mini aggregation on the key value pairs which were generated by map. So once the data is coming in from the combiner, then we have internally a partitioner phase which decides how outputs from combiners are sent to the reducers. Or you could also say that even if I did not have a combiner, partitioner would decide based on the keys and values, based on the type of keys, how many reducers would be required or how many reduce tasks would be required to work on your output which was generated by map task. Now once partitioner has decided that, then your data would be then sorted and shuffled, which is then fed into the reducer. So when you talk about your reducer, it would basically have one or multiple reduce tasks. Now that depends on what partitioner decided or determined for your data to be processed. It can also depend on the configuration properties which have been set to decide how many reduce tasks should be used. Now internally all this data is obviously going through sorting and shuffling so that your reducing or aggregation becomes an easier task. Once we have this done, we basically have the reducer, which is the code for the reducer is provided by the developer, and all the intermediate data has then to be aggregated to give you a final output, which would then be stored on SDFS. And who does this? You have an internal record writer which writes these output key value pairs from reducer to the output files. Now this is how your MapReduce works, wherein the final output data can be not only stored but then read or accessed from SDFS or even used as an input for further MapReduce kind of processing. So this is how it overall looks. So you basically have your data stored on SDFS. Based on input format, you have the splits, then you have record reader which gives your data to the mapping phase, which is then taken care by your mapper function. And mapper function basically means one or multiple map tasks working on your chunks of data. You could have a combiner phase which is optional, which is not mandatory. Then you have a partitioner phase which decides on how many reduce tasks or how many reducers would be used to work on your data. Internally there is sorting and shuffling of data happening, and then basically based on your output format, your record reader will write the output to SDFS directory. Now internally you could also remember that data is being processed locally, so you would have the output of each task which is being worked upon stored locally. However, we do not access the data directly from data nodes, we access it from SDFS, so our output is stored on SDFS. So that is your MapReduce workflow. When you talk about MapReduce architecture, now this is how it would look. So you would have basically a edge node or a client program or an API which intends to process some data. So it submits the job to the job tracker, or you can say resource manager in case of Hadoop Yarn framework, right? Now before this step, we can also say that an interaction with name node would have already happened, which would have given information of data nodes which have the relevant data stored. Then your master processor. So in Hadoop version 1 we had job tracker, and then the slaves were called task trackers. In Hadoop version 2, instead of job tracker you have resource manager, and instead of task trackers you have node managers. So basically your resource manager has to assign the job to the task trackers or node managers. So your node managers, as we discussed in Yarn, are basically taking care of processing which happens on every node. So internally there is all of this work happening by resource manager, node managers, and application master, and you can refer to the Yarn based tutorial to understand more about that. So here your processing master is basically breaking down the application into tasks. What it does internally is once your application is submitted, your application to be run on Yarn processing framework is handled by resource manager. Now forget about the Yarn part as of now. I mean, who does the negotiating of resources, who allocates them, how does the processing happen on the nodes, right? So that's all to do with how Yarn handles the processing request. So you have your data which is stored in HDFS, broken down into one or multiple splits. Depending on the input format which has been specified by the developer, your input splits are to be worked upon by your one or multiple map tasks which will be running within the container on the nodes. Basically, you have the resources which are being utilized. So for each map task, you would have some amount of RAM which will be utilized, and then further the same data which has to go through reducing phase, that is your reduce task, will also be utilizing some RAM and CPU cores. Now internally you have these functions which take care of deciding on number of reducers, doing a mini reduce, and basically reading and processing the data from multiple data nodes. Now this is how your MapReduce programming model makes parallel processing work, or processes your data which is stored across multiple machines.
Map execution in a distributed two-node environment. The mappers on each of the nodes are assigned to each input split of box. Based on the input format, the record reader reads the split as a key value pair. The map function is applied to each record to then return 0 or more new records. These intermediate outputs are stored in the local file system. Thereafter, a partitioner assigns the records to the reducer. In the shuffling phase, the intermediate key value pairs are exchanged by all nodes. The key value pairs are then sorted by applying the key and reduce function. Again, the output is stored in HDFS based on the specified output file format. The essentials of each MapReduce phase are shown on the screen. The job input is specified in key value pairs. Each job consists of two stages. First, a user-defined map function is applied to each input record to produce a list of intermediate key value pairs. Second, a user-defined reduce function is called once for each distinct key in the map output. Then, the list of intermediate values associated with that key is passed. The essentials of each MapReduce phase are as follows. First, the number of reduced tasks can be defined by the users. Second, each reduced task is assigned a set or record groups, that is, intermediate records corresponding to a group of keys. Third, for each group, a user-defined reduce function is applied to the recorded values. And four, the reduced tasks are read from every map task, and each read returns the record groups for that reduce task. Reduce phase cannot start until all mappers have finished processing. So, combining your output is an important step once all the tasks are completed. MapReduce job. A job is a MapReduce program that causes multiple map and reduce functions to run parallelly over the life of the program. Many copies of map and many copies of reduce functions are forked for parallel processing across the input dataset. A task is a map or reduce function executed on a subset of this data. With this understanding of job and task, the application master and node manager functions become easier to comprehend. First, the application master is responsible for the execution of a single application or MapReduce job. It divides the job request into tasks and assigns those tasks to node managers running on one or more slave nodes. The node manager has a number of dynamically created resource containers. The size of a container depends on the amount of resources it contains, such as memory, CPU, disk, and network I/O. It executes map and reduce tasks by launching these containers when instructed to by the MapReduce application master. MapReduce and associated tasks. The map process is an initial step to process individual input records in parallel. The reduce process is all about summating the output with a defined goal as coded in the business logic. The node manager keeps track of individual map tasks and can run in parallel. A map job runs as part of a container execution by Node Manager on a particular data node within a cluster. The application master keeps track of a MapReduce job. The Hadoop MapReduce job work interaction. Initially, a Hadoop MapReduce job is submitted by a client in the form of an input file or a number of input splits of files, each containing data. The MapReduce application master will then distribute the input split to separate node managers. The MapReduce application master then coordinates with those node managers. The MapReduce application master will now resubmit the task to an alternate node manager if that data node should fail. The resource manager gathers the final output and informs the client of success or failure status. Let's look at the characteristics of MapReduce. MapReduce is designed to handle very large-scale data in the range of petabytes and exabytes. It works well on write once and read many data sets, also known as worm data. MapReduce allows parallelism without mutexes. The map and reduce operations are performed by the same processor. Those operations are provisioned near the data as data locality is preferred. In other words, we will move the application to the data and not the other way around. Commodity hardware and storage is leveraged in MapReduce to keep things cost-effective. And the runtime takes care of splitting and moving data for operations. Some of the real-time uses of MapReduce are as follows. Simple algorithms such as grep, text indexing, and reverse indexing. Such things as data-intensive computing, which would include sorting large and small sets of data, stream data, and structured data. Data mining operations such as Bayesian classification, which you'll study later. And search engine operations such as keyword indexing, ad rendering, and page ranking. Enterprise analytics to ensure the business is operating smoothly and with the best decision-making data available. Gaussian analysis for locating extraterrestrial objects in astronomy, which uses very large data sets. And semantic web and Web 3.0 indexing and operations. Data types in Hadoop. Data types in Hadoop. The first data type is text. The function of this data type is stored to string data. The int writable data type stores integer data. Long writable, as the name suggests, stores long data. Similarly, other data types are float writable for storing float data and double writable for storing double data. There is also Boolean writable and byte writable data types. Null writable is a placeholder when a value is not needed. This illustration here shows a sample data type that you can create on your own. This data type will need you to implement a writable interface. As you can see, writable will define a deserialization or serialization protocol. Every data type in Hadoop is a writable. Writable comparable will define your sort order. All keys must be of this type, but not value. Then int writable and long writable, and the various concrete classes that you'll define for your different data types. Lastly, sequence files refers to a binary encoded with a sequence of key value pairs. Input format in MapReduce. MapReduce can specify how its input is to be read by defining an input format. The table lists some of the classes of input formats provided by the Hadoop framework. Let's look at each of them. The first class is key value text input format, which is used to create a single key value pair per line. Text input format is used to create a program that considers a key as the line number and a value as the line itself. N-line input format is similar to text input format, except that there are n number of lines that make an input split. Multi-file input format is used to implement an input format that aggregates and for the class sequence file input format to be implemented, the input file must be a Hadoop sequence file, which contains serialized key value pairs. we set up the environment for MapReduce development. First, let's ensure that all Hadoop services are live and running. This can be verified in 2 steps. First, use the command jps. As shown, type sudo jps, and then look for all 5 services that you need: name node, data node, node manager, resource manager, and secondary name node. There may be additional services that are used by a Hadoop cluster, but these are the ones that we require as core services. Next, let's look at uploading big data and small data. The command to upload any data, big or small, from the local file system to HDFS is Hadoop -fs -copy from local and then the source file address and the destination file address. Now let's look at the steps of building a MapReduce program. First, determine if the data can be made parallel and solved by using MapReduce. For example, you need to analyze whether the data is write once, read many, or worm type data in nature. Then design and implement a solution as a mapper and then reducer class within your code. Compile the source code with Hadoop core and package the code as a jar executable. Configure the application job as the number of mapper and reducer tasks and to the number of input and output streams. Then load the data or use it on previously available data and then launch and monitor the job. You can then study the results and repeat any of the previous steps as needed. The Hadoop MapReduce requirements. The user or developer is required to set up the framework with the following parameters: the locations of the job input in the distributed file system, the location of the job output in the distributed file system, the input format to use, the output format to use. Define a class containing the map function, and then a separate class containing the reduce function, which is optional. If a job does not need a reduce function, there is no need to specify a reducer class in your code. The framework will partition the input, schedule, and execute map tasks across the cluster. If requested, it will sort the results of the map task, and it will execute the reduced tasks with the map output. The final output will be moved to the output directory, and the job status then reported to the user. Set of classes. This image shows the set of classes under the user supply and the framework supply. The user supply refers to the set of Java classes and the methods provided to a Java developer for developing Hadoop MapReduce applications. The framework supply refers to defining the workflow of a job, which is followed by all Hadoop services. As shown in the image, the user provides the input location and the input format as required by the program logic. Once the resource manager accepts the input, a specific job is divided into tasks by the application master. Each task is then assigned to an individual node manager. Once the assignment is complete, the node manager will start the map task. It performs shuffling, partitioning, and sorting for individual map outputs. Once the sorting is complete, the reducer starts the merging process. This is also called the reduce task. The final step is collecting the output, which is performed once across all the individual tasks once they're completed. This reduction is based on programming logic. Let's look at MapReduce responsibilities. The basic user or developer responsibilities of MapReduce are 1. Setting up the job, 2. Specifying the input location, and 3. Ensuring that the input is in the expected format and location. The framework responsibilities of MapReduce are distributing jobs among the application master and node manager nodes of the cluster, running the map operation, then performing the shuffling and sorting operations. Next are the optional reducing phases, and finally placing the output in the output directory and informing the user of the job completion status. We create a new project. Let's see how we would create a new project. First, make sure Eclipse is installed on your system. Once it's installed, you can create a new project and add the essential jar files to run a MapReduce program. Then, to create a new project, click the File menu, select New Project, or alternatively, press Ctrl-N to start the wizard of a new Eclipse project. The screen shows the new project and select wizard options for the first step. In step number 2, you would select a Java project from the list. Then click the Next button to continue. Step 3, the newly created project has to have a name. In this case, we'll type the project name as word count and click the Next button to continue. In step number 4 of your new project, you will now include jar files from the Hadoop framework to ensure that the programs locate the dependencies to one location. And in step number 5, you will add the essential jar files. To locate these, go to the Libraries tab and click the Add External Jars button to add the essential jar files. After adding the jar files, click the Finish button to complete the project successfully. Next, we'll check the Hadoop environment to ensure we have MapReduce. It is important to check whether the machine setup can perform MapReduce operations. To verify this, use the example jar files that are deployed by a Hadoop installation. This can be run by running the command shown on the screen. Before executing this command, ensure that the words.txt file resides in the data/first location. In the on-screen example, you see the Hadoop jar command being executed, passing it the Hadoop examples.jar file set, word count, and then data/first/words.txt as the input, and data/first/output as the selected output. Advanced MapReduce. Hadoop MapReduce uses data types to work with user-given mappers and user-given reducers. The data is read from files into the mapper and emitted by mappers to the reducers. The processed data is sent back by the reducers. Data emitted by reducers goes into output files. At every step, data is stored in Java objects. Let's now understand the writable data types in Advanced MapReduce. In the Hadoop environment, all input and output objects across the network must obey the writable interface, which allows Hadoop to read and write data in a serialized form for transmission. Let's look at Hadoop interfaces in some more detail. The interfaces in Hadoop are writable and writable comparable. As you've already seen, a writable interface allows Hadoop to read and write data in a serialized form for transmission. A writable interface consists of two methods, read and write fields. A writable comparable interface extends the writable interface so that the data can be used as a key and not as a value. As shown here, the writable comparable implements two methods, compare to and hashcode. Output formats in MapReduce. Now that you've completed the input formats in MapReduce, let's look into the classes for the MapReduce output format. The first class is default output format, which is text output format. It writes records as lines of text. Each key value pair is separated by a tab character. This can be customized by using the MapReduce text output format.separator property. The corresponding input format is key value text input format. Sequence file output format writes sequence files to save on output space. This represents a very compact and compressed version of normal data blocks. Sequence file as binary output format is responsible for writing key value pairs that are in raw binary format into a sequential file container. and map file output format writes map files as the output. The keys in a map file are added in a specific order. The reducer then emits keys in that sorted order. Multiple text output format writes data to multiple files whose names are derived from the output keys and multiple
values.
Sequence file output format creates output in multiple files in a compressed form. Let's look at distributed caching. A distributed cache is a Hadoop feature to cache files that are needed by the applications. A distributed cache will help boost efficiency when a map or reduce task needs access to common data. It allows a cluster node to read the imported files from its local file system instead of retrieving the files from other cluster nodes in the environment. It allows both single files and archives such as zip and tar.gz. It copies files only to slave nodes. If there are no slave nodes in the cluster, then distributed cache copies the files to the master node. It allows access to the cached files from mapper or reducer applications to make sure that the current working directory is added into the application path, and allows referencing of the cached files as though they were present in the current working directory, vastly speeding up access. Using distributed cache. Step 1. First, set up the cache by copying the requisite files to the file system as shown here. Here we see a bin/hadoop fs command using a -copy from local of the file lookup.dat to hdfs myapp/lookup.dat. This shows us that there is currently no file or directory of that name. The Hadoop fs copy from local, remember, will take a file from your local file system and place it in the target directory within the hdfs file system. Using distributed cache. Step 2. Set up the application's job conf as shown in the example. In this case, we're setting up a new instance of job by creating a new instance of job conf. We then will call a distributed cache add cache file method and create a new URI specifying the location, in this case myapp lookup.dat with the file name of lookup.dat. In the same way, each of the different commands here shows you creating a cache entry for zip files, jar files, tar files, tgz, and gz files. In step 3 of setting up your distributed cache, you will use the cache files in the mapper or reducer class that you create. Once the private path and configure information is in your program, you simply declare an instance of file called f, specifying the new file along with the parameter of .map.zip/some file in zip.txt. This will map your file into the distributed cache. Joins in MapReduce. Joins are relational constructs that can be used to combine relations. In MapReduce, joins are applicable in situations where you have two or more datasets you want to combine. A join is performed either in the map phase or later on in the reduce phase by taking advantage of the MapReduce sort-merge architecture. The various join patterns available in MapReduce are reduce side join, replicated join, composite join, and Cartesian product. A reduced side join is used for joining two or more large datasets with the same foreign key with any kind of join operation. A replicated join is a map side join that works in situations where one of the datasets is small enough to cache, thus vastly improving its performance. A composite join is a map side join used on very large formatted input datasets, sorted and partitioned by a foreign key. And lastly, a Cartesian product is a map side join where every single record paired up with another full dataset. This style of join typically takes a significantly longer period of time to execute. A reduced side join works in the following ways. The mapper first prepares for join operations. It takes each input record from every dataset and emits a foreign key record pair. The reducer then performs a join operation where it collects the values of each input group into temporary lists. The temporary lists are then iterated over, and the records from both sets are now joined. A reduce-side join should be used in the following conditions. When multiple large datasets are being joined by a foreign key, or when flexibility is needed to execute any join operation, or when a large amount of network bandwidth is available as we'll be moving data across the network, and also when there is no limitation on the size of datasets. The SQL analogy of a reduce-side join is given on the screen. In the output of a reduce-side join, the number of part files equals the number of reduced tasks. So if you have 10 reduced tasks, you will have 10 separate part files. Replicated joins. A replicated join is a map-only pattern, in other words, does not use the reduce phase, and works as follows. It reads all files from the distributed cache, and then stores them in in-memory lookup tables. The mapper processes each record and joins it with the data stored in memory. There is no data shuffled to the reduce phase. The mapper gives the final output part. This type of join is typically very quick. Replicated joins should be used when all datasets, except for the largest one, can fit into the main memory of each map task that is limited by the size of your Java virtual machine or JVM heap size. When there is a need for an inner join or a left-outer join, with the large input dataset being the left part of the operation, a SQL analogy of this type of replicated join is given on the screen. In the output of a replicated join, the number of part files equal the number of map tasks. And again, as this is using memory as one side of the join, it is typically much faster. A composite join is a map-only pattern, working in the following ways. All datasets are divided into the same number of partitions. Each partition of dataset is sorted by a foreign key, and all of the foreign keys reside in the associated partition of each dataset. Two values are retrieved from the input tuple associated with each dataset based on the foreign key and the output to the file system. This type of join is typically very lengthy, and depending on the size of your datasets can run for a very long time. The composite join should be used when all datasets are sufficiently large and when there is a need for an inner join or a full outer join. A SQL analogy of a composite join is displayed on the screen. In the output of a composite join, the number of part files equal the number of map tasks. The Cartesian product. A Cartesian product is a map-only pattern that works in the following ways. Datasets are split into multiple partitions. Each partition is fed to one or more mappers. For example, in the image shown here, split A-1 and split A-2 are fed to 3 mappers each. A record reader will read every record of input splits associated with the mapper, and the mapper simply pairs every record of a dataset with every record of all other datasets. The Cartesian product should be used when there is a need to analyze relationships between all pairs of individual records, and when there are no constraints on the execution time, as these can take a long time. In the output of a Cartesian product, every possible tuple combination from the input records is represented.
To install Eclipse in the Ubuntu desktop 14.04, open Ubuntu Software Center. Type Eclipse in the search bar as shown on the screen. Select Eclipse from the list. Next, click the Install button to continue. Once Eclipse is installed in your system, create a new project and add the essential jar files to run MapReduce programs. To create a new project, click the File menu. Select New Project. Alternatively, press Ctrl-N to start the wizard of a new project. Select Java Project from the list. Then click the Next button to continue. Type the project name as word count and click the Next button to continue. Include jar files from the Hadoop framework to ensure the programs locate the dependencies to one location. Under the Libraries tab, click the Add External Jars button to add the essential jar files. After adding the jar files, click the Finish button to create the project successfully. Setting up Eclipse environment for MapReduce. In this demo, you will learn to set up an Eclipse environment to execute a MapReduce program. Double-click the Eclipse exe file to start the Eclipse environment. You will be asked for the workspace where the program will be kept. Click OK. As you can see, there are multiple projects already present, and these projects have their project files and other details. You can also refer to any of the old projects. For the purpose of this demo, let's create a new project. Create a new project. Click File, New, Java Project. Give the name of the project. Let's say Simplilearn. Click Next. Finish. It will create a Simplilearn folder for you. You can see that an SRC directory and a JRE system library are available for you. Now you need to import a few jar files through which Eclipse will understand Hadoop program. To import jar files, perform the following steps. Right-click Simplilearn folder. Navigate to Build Path. Select the Configure Build Path. Click Add External Jars. Go to /user/library/Hadoop directory. You can see that there are multiple jars available. You will need Hadoop Common and Hadoop Core, which you will find inside the Client 0.20 directory. You will notice Hadoop Common and Hadoop Core.jar file. Select the files Hadoop Common and Hadoop Core. Click Apply, and then OK. You will notice these jar files appearing in your reference library directory. Now you need to create a new class in this project where you will write your first program. Right-click the SRC folder. Navigate to New, Class. Give the name of the class file, which can be word count in this case. Click Finish. This has created a blank file, wordcount.java. This brings you to the end of the demo. In this demo, you have learned to set up an Eclipse environment, create a project, and the steps to import jar files. You have also learned to write a program in a class. Running MapReduce program. In this demo, you will learn how to write a MapReduce program in the Eclipse environment. Let's import all the Hadoop libraries that are required to execute this program. In this program, you will calculate the number of times each word occurs in a file that resides in the HDFS directory. You will write two functions, mapper and reducer, that will help you to achieve this task. In the main function, you will have to define the properties and configurations to run a MapReduce program. After you finish writing the program, right-click Simplilearn Project Directory, click Export, and select jar file under Java. Type the name of the jar file. You can provide any name of your choice. Let's keep it wordcount.jar in this case. Click Finish. Since the file already exists, you will have to overwrite it. So, click Yes. It will create the file in the local directory. You can see the file wordcount.jar in the directory. In order to run this program, let's type Hadoop jar, and then the name of the jar file, wordcount.jar, that we have just created. Then, type the name of the class file. It is inside the Simplilearn package, .wordcount. Now you need to provide input HDFS path, which is simplilearn/simplilearn.txt. You also need to provide an output path, which can be in simplilearn/out_simplylearn. This out_simplylearn will be a new directory that will be created in HDFS. Now let's go to Hue. Click simplilearn.txt. Notice that the operation is done on the simplilearn.txt file. Let's come out of it. You will notice that there is a new directory, out_simplylearn, which has just been created. This file will have all the counts of the words. This brings you to the end of this demo. You have now learned to write a MapReduce program and run it.
It is important to check whether the machine setup can perform MapReduce operations. To verify this, use the example jar files deployed by Hadoop. This can be done by running the command shown on the screen. Before executing this command, ensure that the words.txt file resides in the data/first location. This image shows the MapReduce version 2.7 architecture comprising Yarn. Hadoop MapReduce uses data types to work with user-given mappers and reducers. The data is read from files into mappers and emitted by mappers to reducers. Processed data is sent back by the reducers. Data emitted by reducers goes into output files. At every step, data is stored in Java objects. Let us now understand the writable data types in advanced MapReduce. In the Hadoop environment,
All the input and output objects across the network must obey the writable interface, which allows Hadoop to read and write in a serialized form for transmission. Let's look at Hadoop interfaces in some more detail. The interfaces in Hadoop are writable and writable comparable. As you've already seen, a writable interface allows Hadoop to read and write data in a serialized form for transmission. A writable interface consists of two methods. Read and write fields are shown here.
A writable comparable interface extends the writable interface so the data can be used as a key and not as a value. As shown here, the writable comparable implements two methods, compare to and hashcode.
So let's have a quick demo on MapReduce and see how it works on a Hadoop cluster. Now we have discussed briefly about MapReduce, which contains mainly two phases, that is your mapping phase and your reducing phase. And mapping phase is taken care by your mapper function, and your reducing phase is taken care by your reducer function. Now in between we also have sorting and shuffling, and then you have other phases, which is partitioner and combiner, and we will discuss about all those in detail in later sessions. But let's have a quick demo on how we can run a MapReduce, which is already existing as a package jar file within your Apache Hadoop cluster or even in your Cloudera cluster. Now we can build our own MapReduce programs. We can package them as jar, transfer them to the cluster, and then run it on a Hadoop cluster on Yarn, or we could be using already provided default programs. So let's see where they are. Now these are my two machines which I have brought up, and basically this would have my Apache Hadoop cluster running. Now we can just do a simple start-all.sh. Now I know that this script is deprecated and it says instead use start DFS and start yarn, but then it will still take care of starting off my cluster on these two nodes, where I would have one single name node, two data nodes, one secondary name node, one resource manager, and two node managers. Now if you have any doubt in how this cluster came up, you can always look at the previous sessions where we had a walkthrough in setting up a cluster on Apache, and then you could also have your cluster running using less than 3 GB of your total machine RAM, and you could have an Apache cluster running on your machine. Now once this cluster comes up, we will also have a look at the web UI, which is available for name node and resource manager. Now based on the settings what we have given, our UIs will show us details of our cluster, but remember the UI is only to browse. Now here my cluster has come up. I can just do a JPS to look at Java related processes, and that will show me what are the processes which are running on C1, which is your data node, resource manager, node manager, and name node. And on my M1 machine, which is my second machine which I've configured here, I can always do a JPS, and that shows me the processes running, which also means that my cluster is up with two data nodes with two node managers. And here I can have a look at my web UI. So I can just do a refresh, and the same thing with this one, just do a refresh. So I had already opened the web pages. So you can always access the web UI using your name node's host name and 570 port. It tells me what is my cluster ID, what is my block pool ID. It gives you information of what is the space usage, how many live nodes you have, and you can even browse your file system. So I have put in a lot of data here. I can click on browse the file system, and this basically shows me multiple directories, and these directories have one or multiple files which we will use for our MapReduce example. Now if you see here, these are my directories which have some sample files, although these files are very small, like 8.7 kilobytes. If you look into this directory, if you look into this, I have just pulled in some of my Hadoop logs and I have put it on my SDFS. These are a little bigger files, and then we also have some other data which we can see here, and this is data which I've downloaded from web. Now we can either run a MapReduce on a single file or in a directory which contains multiple files. Let's look at that. Before looking a demo on MapReduce, also remember MapReduce will create a output directory, and we need to have that directory created. Plus we need to have the permissions to run the MapReduce job. So by default, since I'm running it using admin ID, I should not have any problem. But then if you intend to run MapReduce with a different user, then obviously you will have to ask the admin, or you will have to give the user permission to read and write from SDFS. So this is the directory which I have created, which will contain my output once the MapReduce job finishes. And this is my cluster file system. If you look on this UI, this shows me about my yarn, which is available for taking care of any processing. It as of now shows that I have total of 8 GB memory and I have 8 vCores. Now that can be depending on what configuration we have set or how many nodes are available. We can look at nodes which are available, and that shows me I have 2 node managers running. Each has 8 GB memory and 8 vCores. Now that's not true actually, but then we have not set the configurations for node managers, and that's why it takes the default properties, that is 8 GB RAM and 8 vCores. Now this is my yarn UI. We can also look at scheduler, which basically shows me the different queues if they have been configured, where you will have to run the jobs. We'll discuss about all these later in detail. Now let's go back to our terminal and let's see where we can find some sample applications which we can run on the cluster. So once I go to the terminal, I can, well, submit the MapReduce job from any terminal. Now here I know that my Hadoop related directory is here, and within Hadoop you have various directories. We have discussed that in binaries you have the commands which you can run. In sbin you basically have the startup scripts, and here you also notice there is a share directory in the end. If you look in the share directory, you would find Hadoop, and within Hadoop you have various subdirectories in which we will look for MapReduce. Now this MapReduce directory has some sample jar files which we can use to run a MapReduce on the cluster. Similarly, if you are working on a Cloudera cluster, you would have to go into opt Cloudera parcel cdh/lib, and in that you would have directories for SDFS MapReduce or SDFS yarn, where you can still find the same jars. It is basically a package which contains your multiple applications. Now how do we run a MapReduce? We can just type in Hadoop and hit enter, and that shows me that I have an option called jar, which can be used to run a jar file. Now at any point of time, if you would want to see what are the different classes which are available in a particular jar, you could always do a jar -xvf. For example, I could say jar xvf, and I could say user local Hadoop share Hadoop MapReduce, and then list down your jar file. So I'll say Hadoop MapReduce examples, and if I do this, this should basically unpack it to show me what classes are available within this particular jar. And it has done this. It has created a meta file and it has created a org directory. We can see that by doing a ls, and here if you look in ls org, since I ran the command from a home directory, I can look into org Apache Hadoop examples, which shows me the classes which I have, and those classes contain which mapper or reducer classes. So it might not be just mapper and reducer, but you can always have a look. So for example, I am targeting to use word count program, which does a word count on files and gives me a list of words and how many times they occur in a particular file or in set of files. And this shows me that what are the classes which belong to word count. So we have a int sum reducer. So this is my reducer class. I have tokenizer mapper, that is my mapper class, right? And basically this is what is used. These classes are used if you run a word count. Now there are many other programs which are part of this jar file, and we can expand and see that. So I can say Hadoop jar and give your path. So I'll say Hadoop jar user local Hadoop share Hadoop MapReduce examples, and if I hit on enter, that will show me what are the inbuilt classes which are already available. Now these are certain things which we can use. Now there are other jar files also. For example, I can look at Hadoop, and here we can look at the jar files which we have in this particular path. So this is one Hadoop MapReduce examples which you can use. You can always look in other jar files, like you can look for Hadoop MapReduce client, job client, and then you can look at the test one. So that is also an interesting one. So you can always look into Hadoop MapReduce client, job client, and then you have something ending with tests. So if I would have tried this one using my Hadoop jar command, so in my previous example, when we did this, it was showing me all the classes which are available, and that already has a word count. Now there are other good programs which you can try, like TerraGen to generate dummy data, TerraSort to check your sorting performance, and so on, and TerraValidate to validate the results. Similarly, we can also do a Hadoop jar, as I said, on Hadoop MapReduce. I think that was client, and then we have job client, and then test jar. Now this has a lot of other classes which can be used, or programs which can be used for doing a stress testing or checking your cluster status and so on. One of them, interesting one, is test the FSIO. But let's not get into all the details in first instance. Let's see how we can run a MapReduce. Now if I would want to run a MapReduce, I need to give Hadoop jar and then my jar file, and if I hit on enter, it would say it needs the input and output. It needs which class you want to run. So for example, I would say word count, and again if I hit on enter, it tells me that you need to give me some input and output to process. And obviously this processing will be happening on cluster, that is our yarn processing framework, unless and until you would want to run this job in a local mode. So there is a possibility that you can run the job in a local mode, but let's first try how it runs on the cluster. So how do we do that? Now here I can do a hdfs ls / command to see what I have on my SDFS. Now through my UI, I was already showing you that we have set of files and directories which we can use to process. Now we can take up one single file. So for example, if I pick up new data, and I can look into the files here, what we have, and we can basically run a MapReduce on a single file or multiple files. So let's take this file, whatever that contains, and I would like to do a word count so that I get a list of words and their occurrence in this file. So let me just copy this. Now I also need my output to be written, and that will be written here. So here, if I want to run a MapReduce, I can say Hadoop, which we can pull out from history. So Hadoop jar word count. Now I need to give my input, so that will be new data, and then I will give this file which we just copied. Now I'm going to run the word count only on a single file, and I will basically have my output which will be stored in this directory, the directory which I have created already, mr output. So let's do this output, and this is fair enough. Now you can give many other properties. You can specify how many map jobs you want to run, how many reduce jobs you want to run. Do you want your output to be compressed? Do you want your output to be merged? Or many other properties can be defined when you are specifying word count, and then you can pass in an argument to pass properties from the command line which will affect your output. Now once I go ahead and submit this is basically running a simple inbuilt MapReduce job on our Hadoop cluster. Now obviously internally it will be looking for name node. Now we have some issue here, and it says the output already exists. What does that mean? So it basically means that Hadoop will create an output for you. You just need to give a name, but then you don't need to create it. So let's append the output with number 1, and then let's go ahead and run this. So I've submitted this command. Now this can also be run in background if you would want to run multiple jobs on your cluster at the same time. So it takes total input paths to process is 1. So that is, there is only one split on which your job has to work. Now it will internally try to contact your resource manager, and basically this is done. So here we can have a look, and we can see some counters here. Now what I also see is for some property which it is missing, it has run the job, but it has run in a local mode. It has run in a local mode. So although we have submitted, so this might be related to my yarn settings, and we can check that. So if I do a refresh, when I have run my application, it has completed. It would have created an output, but the only thing is it did not interact with your yarn. It did not interact with your resource manager. We can check those properties, and here if we look into the job, it basically tells me that it went for mapping and reducing. It would have created an output. It worked on my file, but then it ran in a local mode. It ran in a local mode. So MapReduce, remember, is a programming model, right? Now, if you run it on Yarn, you get the facilities of running it on a cluster where Yarn takes care of resource management. If you don't run it on Yarn and run it on a local mode, it will use your machine's RAM and CPU cores for processing. But then we can quickly look at the output, and then we can also try running this on Yarn. So if I look into my HDFS and if I look into my output, MR output, that's the directory which was not used actually. Let's look into the other directory which is ending with 1, and that should show me the output created by this MapReduce. Although it ran in a local mode, it fetched an input file from your SDFS and it would have created output in SDFS. Now that's my part file which is created, and if you look at part minus R minus these zeros, if you would have more than one reducer running, then you would have multiple such files created. We can look into this. What does this file contain? Which should have my word count, and here I can say cat, which basically shows me what is the output created by my MapReduce. Let's have a look into this. So the file which we gave for processing has been broken down, and now we have the list of words which occur in the file plus a count of those words. So if there is some word which is more, then it shows me the count. So this is a list of my words and the count for that. So this is how we run a sample MapReduce job. I will also show you how we can run it on Yarn. Now let's run MapReduce on Yarn, and initially when we tried running a MapReduce, it did not hit Yarn, but it ran in a local mode, and that was because there was a property which had to be changed in MapReduce-site file. So basically, if you look into this file, the error was that I had given a property which says mapred.framework.name, and that was not the right property name, and it was ignored, and that's why it ran in a local mode. So I changed the property to mapreduce.framework.name, restarted my cluster, and everything should be fine now. And that mapred-site file has also been copied across the nodes. Now to run a MapReduce on a Hadoop cluster so that it uses Yarn, and Yarn takes care of resource allocation on one or multiple machines. So I'm just changing the output here, and now I will submit this job, which should first connect to the resource manager. And if it connects to the resource manager, that means our job will be run using Yarn on the cluster rather than in a local mode. So now we have to wait for this application to internally connect to resource manager, and once it starts there, we can always go back to the web UI and check if our application has reached Yarn. So it shows me that there is one input part to be processed. That's my job ID, that's my application ID, which you can even monitor status from the command line. Now here the job has been submitted, so let's go back here and just do a refresh on my Yarn UI, which should show me the new application which is submitted. It tells me that it is in accepted state. Application master has already started, and if you click on this link, it will also give you more details of how many map and reduce tasks would run. So as of now, it says the application master is running. It would be using this node which is M1. We can always look into the logs. We can see that there is a one task attempt which is being made. And now if I go back to my terminal, I will see that it is waiting to get some resources from the cluster. And once it gets the resources, it will first start with the mapping phase, where the mapper function runs. It does the map tasks, one or multiple depending on the splits. So right now we have one file and one split, so we will have just one map task running. And once the mapping phase completes, then it will get into reducing, which will finally give me my output. So we can be toggling through these sessions. So here I can just do a refresh to see what is happening with my application. Is it proceeding? Is it still waiting for resource manager to allocate some resources? Now, just a couple of minutes back, I tested this application on Yarn, and we can see that my first application completed successfully. And here we will have to give some time so that Yarn can allocate the resources. Now, if the resources were used by some other application, they will have to be freed up. Now, internally, Yarn takes care of all that, which we will learn more detail in Yarn, or you might have already followed the Yarn based session. Now here we will have to just give it some more time, and let's see if my application proceeds with the resources what Yarn can allocate to it. Sometimes you can also see a slowness in what web UI shows up, and that can be related to the amount of memory you have allocated to your nodes. Now for Apache, we can have less amount of memory and we can still run the cluster. And as I said, the memory which shows up here, 16 GB and 16 cores, is not the true one. Those are the default settings, right? But then my yarn should be able to facilitate running of this application. Let's just give it a couple of seconds and then let's look into the output here. Again, I had to make some changes in the settings because our application was not getting enough resources, and then basically I restarted my cluster. Now let's submit the application again to the cluster, which first should contact the resource manager, and then basically the map and reduce process should start. So here I've submitted an application. It is connecting to the resource manager, and then basically it will start internally an app master, that is application master. It is looking for the number of splits, which is 1. It's getting the application ID, and it basically then starts running the job. It also gives you a tracking URL to look at the output. And now we should go back and look at our yarn UI if our application shows up here, and we will have to give it a couple of seconds when it can get the final status change to running, and that's where my application will be getting resources. Now if you closely notice here, I have allocated specific amount of memory, that is 1.5 GB for node manager on every node, and I have basically given 2 cores each, which my machines also have, and my yarn should be utilizing these resources rather than going for default. Now the application has started moving, and we can see the progress bar here, which basically will show what is happening. And if we go back to the terminal, it will show that first it went in deciding map and reduce. It goes for map. Once the mapping phase completes, then the reducing phase will come into existence, and here my job has completed. So now it has basically used, we can always look at how many map and reduce tasks were run. It shows me that there was 1 map and 1 reduce task. Now with the number of map tasks depends on the number of splits, and we had just 1 file which is less than 128 MB, so that was 1 split to be processed, and reduce task is internally decided by the reducer, or depending on what kind of property has been set in Hadoop config files. Now it also tells me how many input records were read, which basically means these were the number of lines in the file. It tells me output records, which gives me the number of total words in the file. Now there might be duplicates, and that which is processed by internal combiner, further processing or forwarding that information to reducer, and basically reducer works on 335 records, gives us a list of words and their count. Now if I do a refresh here, this would obviously show my application is completed. It says succeeded. You can always click on the application to look for more information. It tells me where it ran. Now we do not have a history server running as of now, otherwise we can always access more information. So this leads to history server where all your applications are stored. But I can click on this attempt tasks, and this will basically show me the history URL, or you can always look into the logs. So this is how you can submit a sample application which is inbuilt, which is available in the jar on your Hadoop cluster, and that will utilize your cluster to run. Now you could always, as I said, when you're running a particular job, remember to change the output directory, and if you would not want it to be processing a single individual file, you could also point it to a directory. That basically means it will have multiple files, and depending on the file sizes, there would be multiple splits, and according to that, multiple map tasks will be selected. So if I click on this, this would submit my second application to the cluster, which should first connect to resource manager. Then resource manager has to start an application master. Now here we are targeting 10 splits. Now you have to sometimes give a couple of seconds in your machines so that the resources which were used are internally already freed up, so that your cluster can pick it up, and then your yarn can take care of resources. So right now my application is in undefined status, but then as soon as my yarn provides it the resources, we will have the application running on our yarn cluster. So it has already started. If you see, it is going further. Then it would launch 10 map tasks, and the number of reduced tasks would be decided on either the way your data is or based on the properties which have been set at your cluster level. Let's just do a quick refresh here on my yarn UI to show me the progress. Also take care that when you are submitting your application, you need to have the output directory mentioned. However, do not create it. Hadoop will create that for you. Now, this is how you run a MapReduce without specifying properties, but then you can specify more properties. You can look into what are the things which can be changed for your mapper and reducer, or basically having a combiner class which can do a mini reducing, and all those things can be done. So we will learn about that in the later sessions. In this tutorial, we will have some demos on running a MapReduce and processing data to solve some real-time business problems. Now, I have set up some code in Eclipse which can be either tested on your Windows machine by running it in a local mode, or packaging your code in jar, transferring it to your cluster, and then basically running it on your cluster nodes. So we'll see both of these examples. Now let's assume and let's understand about a problem. Say for example, we have a telecom based company which would want to process its data. Say it would want to find out the number of subscribers and the kind of calls they are making. Or for example, let's imagine a online website or a music website where users listen to various tracks. The data gets collected and then basically it has to be processed. So imagine you have a company which is hosting music online, and you have users who either are subscribers or basically create their accounts, listen to different tracks, and then basically use these services. Now, what if I would want to process such data? For example, if I would want to find out what is the number of unique listeners, or number of times the track was shared with other users, or number of times the track was listened to on the radio or in total, or even was skipped on the radio. Now in that case, I would want to process the data to find out information. So we will solve this kind of problem using the MapReduce programming model, the MapReduce approach, which as I explained earlier goes for mapping and then goes for reducing. And in between it has different phases, that is shuffling and sorting. You have your partitioner phase, you have a mini reducer which is your combiner phase. Although all of these intermittent phases are taken care by the framework itself. The developer or the person who is developing the solution is responsible to work on the mapper function and the reducer function. Now for that, we can basically be writing our code to process this data by giving a mapper and a reducer function. Data, we can look into example and say, for example, let me pull out some data here. Let's look in, say, some files I have, and for example in this case it would be this kind of data. Now that magnitude could be anything, right? Now here I have the data which the first column talks as the user ID or the membership ID. The second is the track ID. You have then if the track was shared online. The fourth one is number of times the track was listened to in total, and the fifth one is if a particular track was skipped. Now I could have this data in huge numbers and then I could be processing it, but we will take a simple small example to understand how MapReduce does this. So this is a file which I have already uploaded on the cluster and which will be as my input file. Now let's look at the code. So what we would need is, for this kind of processing, we would first need to understand the data. Now here the first column, as I said, is user ID and second one is track ID, which can then be used to basically process the data. We need to write a mapper class which would emit the track ID from this data. So I have it here, and let me also open up a constant class for this, which is here. So as I mentioned, we will have to write a mapper class which would emit track ID from the data and user IDs with some intermediate key value pairs. Now that is what your mapping phase does. It works on the input splits. It basically does the mapping and it gives you a list of data elements which are nothing but your intermediate key value pairs. To explain it in a simple way, I would say just let's work on this data sequence. So let's create a constant class as shown here. So this is my package. Now I create a class called last fm constants, and then I am here declaring some variables with some constant values for each of the field which I just showed in the file. You have user ID, you have track ID, you have is scrobbled or shared, radio, and is skipped. Now these are my constant which will be used while I process. Then we will have to work on a mapper class which could or which would emit intermediate key value pairs, that is your track ID and user ID. Now how do we do that? So here is an example. So we basically would have a mapper class as it's seen here. This is my mapper class which will be used to process or do the mapping phase. Now here we have the class name which is unique listener and unique listeners mapper, which extends the mapper class. That means I would have to import the relevant packages for my code, which I have done on the top. Here then I have variables, that is track ID, user ID, which use int writable. So Hadoop has its own data types, say int writable, long writable, boolean writable, which are similar to what you have in Java as int, boolean, long. But these data types which are used by Hadoop are basically an implementation of writable and writable comparable interfaces. So those are two interfaces which are then responsible for these classes which we are using as data types in our code. Here we start our map task, which would then consider key, which is an object, value as in text, and then you have your data types, that is int writable, text, and object. We are also handling exception, and then what we do is we work on the file. So we would split it based on the delimiter. Now in my case, the delimiter is a pipe. Then what we do is we set for the track ID using our constants, that is what we have seen here, which is for your user ID, track ID, and so on. And we do the same thing for our user ID. We look into the values and then we basically emit out just the track ID and user ID. That would be my intermediate key value pairs. Now here I am also using a counter named invalid record count. Now that is mainly to count if there are any invalid records which do not exist in the file in an expected format. Now, we don't do this in case of invalid records. If we don't do this, what would happen? If we had invalid records in our file, then our program might fail. And that's the reason I'm using counters.invalidrecord.count, and I'm going to use it for my mapper. Once we have our mapper written, which basically will look into the file and emit the track ID and user ID, then I would write my reducer class. Now this is how my reducer class looks, where I'm saying public static class unique listener reducer, which extends reducer class, and then the data types which it would need. So int writable for the values which it works on. So our reduce task will work on track ID, and this reducer class is to aggregate the results. So we cannot directly use some reducer as the records we are getting are not unique. The records might be duplicates. It might be the same user with the same membership ID listening to a different track or sharing it. And we cannot be just using a generic reducer. So here we work on the reducer, and this is how my code would look. So what my reducer does, it basically would help me in solving the problem, such as basically aggregating and counting the number of tracks which were shared or listened to, or overall the number of tracks, and then you have your tracks which were skipped. One of the main tasks of your reducer class is on working on the intermediate data which is created by your mapper, or you can say multiple map tasks which would be running on multiple splits on one or multiple nodes, and your reducer's work is to aggregate the result based on the keys. Here we are using set to eliminate duplicate user IDs. Now, once we have written our reducer class, which basically works on the user ID set, it eliminates the duplicate user IDs, and then it basically gives me a count of the track IDs in an aggregated way to solve my use case. Once I've done that, I also need a driver class which basically tells about my overall code. So here we are having a job configuration where I say my name of the job could be unique listeners per track. I'm setting the jar by class, calling it as unique listeners. That's my class. I'm mentioning my mapper. I'm mentioning my reducer. Now, if you notice, I'm not using a combiner class. For this use case, we would not need that. So combiner class is a mini reducer which basically helps in reducing the data or aggregating the data before it reaches the reducer class. I am also talking about the key, which would be using int writable, and then the value, which would also be int writable, as all my values are in numeric. If I had my key in something else, or if I had names instead of user ID, then I could have used text class. I also specify what would be my input and output path, which will be specified as an argument, and then basically I am printing out number of invalid records. So this is my MapReduce program to work on solving our business use case. Also notice I'm using the relevant packages which are being used in the code, and for these packages and for this code to compile, we need to make sure that we have added the right dependencies. Now you could have created your code with POM and using Maven, or based on the classes what you are using, you can always add the jars, the relevant jars to the build path. So here we can look at the build path what I have, and we can see what jars I have used. So the main ones are your commons. I have Hadoop core. Now you can ignore Hive or JSON which I have here. Those are for different applications. So the main is common CLI and Hadoop core depending on what you are using within your application. So that has to be added to your build path. Also we are having the Java 1.8. Now if I wanted to run this application or test it on my local machine, I could have also set up the configurations. However, it is preferred to run the code on a yarn based cluster. If you would want to try it on Windows, then you can always go to the run configuration. You can basically specify your application which you would want to run. You can then say what is your class name. You can be passing in your arguments here, and in your environment you can specify Hadoop as a local IP. However, I suggest package it as jar and run it on a cluster. So what you could do is you could select your class. Now my unique listeners .java class is also getting the constants from last FM constants. So both of them belong to the same project, and I'm using that here for my mapper and for my reducer. So in mapper, I refer to last FM constants where I've given constant values for all of these fields. Once you have your code ready, you can always package it as jar by saying export and select the jar option in Java, click on next, and then you can select your project and give it a name. So I'm pointing into a different jar file, but I can do a browse. I've already packaged it as jar, and you can see I have a jar here. So I can select this, I can say save, and that would be my jar. If I'm making some changes, it will anyways overwrite it. Once you have your jar ready, what you need to do is place it on your cluster. Now I have already done that. I have a cluster here. Let me bring it up. And what we can do is you can use different ways. You can have an Apache cluster. You could have a Cloudera cluster wherein you need to place. So let's get into this. Now here I'm using a already set up lab environment. You can be doing an FTP. You can upload your code using Hue. I have done an FTP from my local machine and uploaded it to the cluster. I could click on web console, which basically gives me a console to try out things. You could, as I said, you need the jar and then you need to push your jar to your cluster. Let me log in here, and once I'm logged in, I am on a edge node which allows me to connect to a cluster which is Cloudera's based, and now I can check on my HDFS path in my user directory. I should have multiple files and directories, and in one of the directories I have placed in this file. So we can look in here, which is sample mr in, and that's my directory where I have the input. So I can look in sample mr in, and the same file which I showed in the beginning, I have uploaded it here, which is the listeners file, which we can even check. So I can say listeners.txt, and I can even do a cat. So this is the file which is already existing here, which has the content which we spoke about, although not huge content, but it is more than enough for us to test our code. And obviously we can upload huge data and then have the same MapReduce program helping us in answering our questions. We also need the jar file, and the jar file should be here, which I have uploaded. So I need to run this. Now to run your MapReduce, you can say Hadoop jar. You will give your jar name, which is this one. Now I need to give my package name with my class name. So I'll say org example Hadoop codes, and then I need to give my class, which is unique listeners. Now if I hit enter here, it will ask me to give an input and output, as my code says to pass in the arguments. So we will pass in the arguments here. So I'll say my directory where I have the data. Now I could be picking up one file or multiple files to process this. So I will say just one file, which is here, and that's my file, which is sample mr in. That is what I want to use. So I'll say sample mr in, and I need to give my file name. So I can say listeners.txt, and then I can give an output which will get created when you run your MapReduce. So I can say sample mr, and then I can say output 1, and this is the directory which will get created, which will have my output. Now you can run this job in this way. You can even run it in a local mode by specifying arguments on the command line. You can give different kind of properties. If you want your MapReduce jobs output to be in a compressed format, you can do all that. So let's run this, and this should connect to the resource manager. The job is processing one input file. It will start with the mapping phase first. Now it looks that the job has failed due to some reason. Let's have a look. I just looked into the job and I realized why it failed. The main reason was I was trying to write an output in the directory to which I don't have access. I need to have access to write the output in a directory to which my user ID has permissions. For this, we will have to submit the job again with the right path where it can write the output. So we can do this. This is my class. I need input. So I'll say, and then we can say sample mr in, and I'm looking for listeners.txt, and I need to give an output which should be in this path, and then we can say sample mr output 1, and then submit the job. Now once I've submitted the job, as I said, it has one input part to process. It is working on one split because the file which we are trying to work on is smaller than the block size. It goes for the mapping phase, and then it goes for reducing, and it's done. So if you carefully look at the MapReduce output here, it says the number of outputs it had to process was just 4. So every line by default is considered as a record, and we had totally 4 lines. The output is basically working on again giving you 4 records, right? Because we are doing a split based on the delimiter. Then this would become an input to combiner if we had a combiner class, but we don't use that. So the output from your map goes to the reduce, which will basically work on the input records and create output records. Now we can have a look at this, the output of this job, which is stored in HDFS, and I can either be giving a complete path, or I can just mention the directory which I used, and that should by default take me to the directory which should have my output. Now based on how many reduce tasks were used, you will have number of part files which show up here. So we have one map and one reduce task. That could have controlled, or that could have been controlled by giving things on the command line. So here I have run it in a yarn mode, where yarn was used to allocate resources for my applications, and we can always check that on the yarn UI, or also by going to say Cloudera manager if that is available. If you're not using Cloudera's cluster, then you can always in Apache cluster go to your yarn, and you can go into the UI wherever your resource manager is running. So that is one option. Or if you have a Cloudera cluster, you can look in application applications, which will show all the applications which were recently run. So this was the thing which failed earlier because of permissions, and this is the one which succeeded. Now I have a job ID which can always take me to the Yarn UI, the history server, where I see how many map and jobs were run. And for further information, you can always go and look into the map and reduce tasks. So this was a map task which ran within a container which was allocated by your Yarn, and we can also look on the node and logs what really happened. You can also look into the reduce task. You can also look at the counters which we were seeing on the command line on how many map and reduce tasks, how many bytes were read, what was the garbage collection time, how much CPU time was spent in milliseconds, and you get all the counters here. You can specifically be looking at counters for map or for reduce. So your Yarn UI helps you to look into for more information. Now if I go back to my console and I have the output file, I can basically look into it by selecting the output file, and I can do a cat, which basically will show me what is my output. So this is my MapReduce, and basically what it has done it has aggregated and pulled out the information for your different listeners based on the data what we have provided. Let's look at one more example of using MapReduce programming model to solve a real-time business case or a problem. Now the problem in hand is that we have some data collected from a telecom giant, and basically we have some sample data here which lists the list of subscribers which are using the services. Now if I look into the file, I have call data records, which basically gives me information about the data collected by a telecom company. So this telecom company keeps records of its subscribers, and it calls this particular file as call data records. Now what does this call data records contain? It basically has a from phone number as the first field. It has the to phone number, that is call being made to a particular number. Then we have the call start time following a timestamp. You have a call end time, and then we have finally if this call was a distance call, or what we call as STD call. Now what we need to do is we need to use our knowledge of MapReduce. We need to use the MapReduce programming model, and we need to come up with a code to find out all the phone numbers, for example, who were making more than 60 minutes of STD calls. Now here the flag 1 basically means it was an STD call, and 0 means it was a local call. How do we do that? Using MapReduce. So this is again a problem where you would want to count through the data, and you would want to aggregate the values to come up with result. So let's look at a sample code for this one. So here I have my Eclipse, and again like a previous example, we are having a class which declares some constants for the fields. So you have phone number with 0, phone number with 1, call start time, call end time, and an STD flag. So these are the constants which I would be using in my code, and here is my main class which will use the MapReduce basically to solve this problem. Now I'm importing the packages, and as I explained earlier, these packages are mainly to make sure that we can use the classes in our code in the right way. So here now the order of your driver class or your mapper and reducer does not matter, right? The first thing what we need is we need a mapper which will do the map task. So here I'm creating a mapper which is tokenizer mapper, and that extends your mapper class. It accepts the data types, that is object, text, and long writable. As explained earlier, these are your data types which are Hadoop specific, and data types like int writable, long writable, boolean writable, and many others depend on the writable and writable comparable interfaces. Now here we start with taking up our phone number. We basically also take duration in minutes, so these are the variables, and I'm using the appropriate data type for those. Then I start writing my map task. Now what does my map task do? It basically works on the string which we have, and it breaks it into individual elements based on a delimiter. Once that is done, then we are also checking if that particular string which we are looking for has a STD flag, because we would want to find out how many customers or how many of them were making phone calls which were more than 60 minutes, and if these calls were STD calls. Then basically I work on the phone number and I set it using the CDR constants, for which we have already created a class using the phone number, call end time, call start time, and I also compute or calculate the long duration, because we need to find out the calls which were more than 60 minutes. Finally, we extract the phone numbers and the duration of the call made by a particular phone number. So this would be my mapper giving an intermediate output, which would then have to be sorted and shuffled and then handed over to reducer. What does my reducer do? It uses the right data types. It basically starts with a sum as 0. It would look into all the keys and values, and wherever it would find keys which are repeating and the duration is more than 60, it would give me an aggregated result. This is my reducer. And finally, we have a driver, as I explained earlier, which has job configuration, your mapper, reducer, and also we are using, just as an example, a combiner class which does not have a class of its own, but it is basically using the same reducer class. Once your code is ready, check if it compiles, check if you have all the dependencies met, and package it as jar, transfer it to the cluster, and run it with or on top of yarn. So what we can do is, I have already moved it here and we can look into this machine. I already have my jar file, which basically also needs a input, which I have already pushed to my cluster. So we can look in for the file which should be existing in sample mr in directory, which is within my user and my name directory, and I have the call data records, which basically shows the data which I was showing in the notepad file. Now I can say Hadoop jar and point it to my jar, which is std subscribers jar. We need to use the package, so I'll say org example Hadoop codes. That's my package, and my class name is std subscribers. So I will say std subscribers dot, and then you need to give your input. So we will say sample mr in, and I will give in a particular file which is call data records.txt, and then we can point it to an output directory which will get created automatically. So I will say output 2, and that should have my result. And like we ran our first example, now I am again running it on one simple file. You can imagine this as you can replace one single file with a directory which has multiple files, where might be the telecom company was already collecting data for a couple of months and they would like to analyze this, and you can run it in this way. So once this is done, we have our output, which can be seen by going into the directory saying sample mr output 2, and again this would have gone for one single reducer. So we can look at whatever we gave as an output. So it was sample mr output 2, and that is my directory. So since this is a directory, my cat command does not work on it. You need to give the file. So the command is by giving the specific file, not by giving the directory. So it is cat sample mr output 2 / part -r, and then you can give 5 zeros, and that should be my out, which should give me an information of which were the users or which were the phone numbers which made calls greater than 60 minutes, and if these calls were STD calls, and what was the duration of the call. So this is how you can use MapReduce programming model to solve your real-time business cases. Always remember, you have to code and create your mapper and reducer function, and rest will be done by the framework. Thank you, and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.